Okay, well, it's a real pleasure to finally be able to have Daniil Rudenko talk about hyperbolic geometry and other beautiful things. Thank you for your title.
Thank you very much. Thank you very much. It's a great pleasure and honor to talk here. Just a few minutes, I will settle it. Okay, that seems right. And I can be without mask.
Yes.
So I will talk about volumes of hyperbolic polytopes, cluster polylogarithms, and the Goncharov depth conjecture. The subject is very classical, especially at the beginning. And we will start with discussing volumes of hyperbolic polytopes, starting with 19th century results. But then we will move on to more modern topics. So volumes of hyperbolic polytopes. So consider a polytope in hyperbolic space. If somebody is comfortable with hyperbolic space, it can be spherical geometry, that's good as well. So how can one compute its volume? So of course, you can express volume as some kind of integral using some model. But this will be kind of a function of all coordinates of vertices. And you might want to express it to some more elementary functions. So here's an example. So if we take dimension 1, and I think here Klein's model, so I have this hyperbolic segment with Q1 and Q2 being the absolute, and A1, A2 being a segment. And then there is a formula for its length, which is here's the volume. And it's basically a logarithm of cross ratio. So what stands there is cross ratio of 4 points. And what is interesting is that we need one mu function, not that mu, to compute this kind of one-dimensional volume, and that's logarithm. So the question is, what happens in higher dimensions? And what new functions will appear if we will try to express volumes of polytopes through as basic functions as possible? So for some reasons, we could not care about even dimensional spaces, because there is a Gauss-Bonnet type formula. In even dimensions, quotations volume reduces to the previous odd dimension. So the next interesting case is dimension 3. So the function which we will first look at, this new function which we need, is called classical polylogarism. And it's just given by this convergent power series inside the unit disk, but it can be analytically extended to the whole plane, and it has kind of monodromy, which is unipotent. And classical polylogarism is, of course, an extension of usual logarithm for n equal to 1. So this number n is called the weight. It is very important, and I will return to it later. So logarithms appeared in the conversation in mail exchange between Leibniz and Bernoulli. And basically, they tried to compute the value of polylogarism at 1, so the sum of inverse powers. And the first person who succeeded, as everybody knows, is Euler computing Lito 1 as pi squared over 6. And the interesting way is he first discovered this equation, which is the first functional equation for dilogarism. And the reason he needed that is because the power series Lito 1, sum of inverse squares, converges very slowly. And it is not possible to guess the answer if you just compute it by hand, even if you are Euler, apparently. So he invented this kind of formula, which expresses Lito 1 through dilogarithm of 1/2, basically. And dilogarithm of 1/2 converges very fast. And so he was able to guess the answer and guess it pi squared over 6. So that's kind of the first equation of polylogarithms appeared. So then Abel continued to study that for I don't know what reason exactly. And he came up with a beautiful functional equation for dilogarism, which is called Abel 5-term relation. We will come to that. So 5 numbers here, which are certain rational functions, are actually 5 cross ratios of 5 points. We'll see at the end of the talk why that matters. And then Kummer continued to study that, and he found certain 9-term relation for these 3, which is already kind of more horrifying. And the next big advance was already in the late 20th century. Goncharov found a more general equation for 3 logarithm. And finding equations for 4 logarithms was really hard. And the simplest one, pretty general, has 931 terms. And it was found with a brutal computer-aided research by Herbert Gungel pretty recently. For Lie 5, no general equation is known.
So it's believed they satisfy beautiful functional equations, but it's a complicated task to find. So polylogarithms have something to do with volumes. And again, the story is very classical because it started with Lobachevsky finding the volume of a polytope in H3, actually a simplex. So he computed a volume of certain kind of simplex I will talk about orthoscheme and expressed it through dilogarithm. And the reason was pretty interesting. So at the moment Lobachevsky was working on hyperbolic Lobachevsky geometry. There was no model yet. And so he, and the consistency of geometry was not known. So his idea was to look at computations of volumes. And he used kind of elementary methods to get some computations done for this kind of special kind of synthesis. And then he obtained from it some identities between integrals, which he could check using classical integration techniques. And then he basically wrote a paper where he explains that he got this correct identities for integrals. And these identities are correct. He called it imaginary geometry, should be not total nonsense. And this was very badly received at that moment in Russia. So he didn't get his appointment in Academy of Science. It is one of the first papers of Lobachevsky. So, and then after more than 100 years, people returned to this question. And in 1947, Bloch and Guillemin proved that a polytope in H5 can be expressed using trilogarithm. And now the formulas are actually horrifying. And they conjecture that volumes in arbitrary odd-dimensional space can be expressed through classical polymorphism, which appeared to be wrong. So already in the next case, H7, that's not true. And you need some extra functions, more complicated functions. And then the story becomes really remarkable because Johannes Bohm, the person who proved this non-result, just 2 years later proved, or almost proved, that in general, one can express volumes through multiple polylogarithms. I will talk about multiple polylogarithms later. So this result is very complicated, very deep, and completely not known. So everybody who quoted Bohm's papers after that, they were saying he had some, like recipe to try to compute volumes, but nobody understood he actually did it. And the reason is probably he never formulated any concrete theorem like that, because at that moment it was not clear multiple polylogarism is a kind of important function. So he just writes a 70-page proof where he kind of writes it as an attempt to compute something. But if you look at it from the modern perspective, you can actually see the theorem proven. And I was working towards this result for maybe 2 years. And when I already had found a proof, only then, chasing through some old references, I found this workable. So I think he's a very sadly kind of forgotten mathematician. He's still alive. He's almost 100 years old in Germany. So I very much want to mention him. So my goal will be to give an explicit formula for volume of an orthoscheme. I will explain what an orthoscheme is. And this immediately implies a result of Bohm in sort of explicit way. And my first goal is to do that. But then, and I will explain the result, but then we will see that this result has a kind of surprising applications to other modern things. In particular, it implies a big part of Goncharov conjectures. So, but this will be the second part of the talk. Okay, so any questions? Okay, so first I need to talk about orthoschemes, and that's again has to do with some forgotten story. So first, what is an orthoscheme? So an orthoscheme in hyperbolic space, Euclidean space, or spherical space, doesn't matter, is a simplex whose faces satisfy certain orthogonality condition. I mean, I stated it here, but the correct way to think about it is that in dimension 1 is just a segment, in dimension 2 it's right angle triangle. And in higher dimensions, it's just higher dimensional generalization of a right angle triangle. So here is a picture of an orthoscheme in a 3-dimensional space. And if you have some, fondness of algebraic topology in your heart, then you might want from a polytope, which reminds you of a right angle triangle, to have a property that its faces are, all faces are right angle triangles. And orthoscheme is exactly that. So if you look at this polytope, it's obtained by taking a segment, perpendicular segment, and perpendicular segment in the third direction, and taking a convex hull, and all its faces are right angle triangles. So, and it's kind of characterized by that. So two facts about order schemes are fundamental. Firstly, all faces and actually all angles, though one need to specify angles are kind of spherical, polytopes in general, are also order schemes. So it's like closed under the stating boundary property. And also any polytope is Caesar congruent to a union of orders. So what that means, you can take a polytope, arbitrary, cut it into simplices, and that can cut simplices into order schemes. And so if I want to express volume of a polytope through some simpler functions, I can restrict myself to order schemes. That's without loss of generality. So that's what Lobachevsky did. So Lobachevsky found a formula for volume of an order scheme. I parameterize this order scheme in a hyperbolic space by 3 dihedral angles at A1, A2, A1, A4, and A4, A3. All others are pi over 90 degrees. So that's an order scheme. And Lobachevsky found a formula for volume of Z. So one can ask, what is the formula for volume of a general tetrahedron? And it appears to be a remarkably hard question, which only in early 21st century was discovered. And I spent more than a year kind of trying to understand this formula for volume of a tetrahedron and its implications. So so at Lobachevsky times, he was able to do just an order scheme. And let me just state the formula of Lobachevsky. So first step is a little horrifying. So we had 3 angles, alpha, beta, gamma, and then we introduce auxiliary angle delta, which looks maybe scary, and its geometric meaning is unclear. And then if you introduce that, then the formula for volume has a pretty nice look. So there is one half imaginary part, which you can ignore, not that important. And then it's just sum of dilogarithms. And all dilogarithms are kind of imaginary exponents of sums and differences of angles, except, and it would be a simple formula, except for this appearance of strange angle delta, which has no geometric meaning. And so the formula is actually hard to prove, and its geometric meaning is unclear. So that's a starting point of my talk, and my goal will be to explain this formula better and to find a generalization to arbitrary dimensions. But this explicitly proves that any polytope in 3-dimensional hyperbolic space can be expressed by dilogarithms. So what? Any questions? So then we come to the next kind of part of the talk, quadrangulation formula. This will be a formula which computes the volume of a general order scheme. So the first question you might have is, why order schemes? What is special about order schemes? And here we again deal with the result. Before order schemes. So we need a supply of functions through which we'll express volume. And the correct supply of functions is multiple polylogarithms. So they are also multi-valued complex analytic functions, which are given by this kind of power series and have unipotent monodromy, which we will not use. So there are 2 kind of parameters. So these functions depend on these integer parameters n1 up to nk. And their sum is called the weight. It has to do with motivic weight and weight in mixed Hodge structures. It's very fundamental. And the number k is much more strange. It's called depth, and that's just the number of arguments. So of course, you like polylogarithms with less number of arguments because they are simpler. But you can think of it as kind of specialization. So here I wrote all polylogarithms of weight 4, and polylogarithms of lower depths can be seen as basically taking limits of polylogarithms of higher depths by degenerating some arguments to 0 or infinity. So a priori, it's not clear why this is important. Why don't we just restrict ourselves to this 4 polylogarithm and work with that? But later on, at the end of the talk, I will start to discuss exactly this kind of depth phenomenon. So for some reason, it's important. But you can think of all these functions as specializations of Lie 1, 1, 1, 1. Okay, so my goal will be to express volume of an order scheme in hyperbolic space via these multiple polylogarithms of weight n. And one can show that you actually cannot do better. You need exactly this supply of functions. So it's easy to show that for each, not so easy. One can show that for each polylogarithm you have polytope exactly that. It's a little complicated, but let me not go into that. So that's a correct supply of functions. Notice also that you will get all volumes of hyperbolic manifolds expressed using the same kind of functions. So it's kind of important for number theory as well. Okay, so now the story of orthoschemes. Why orthoschemes at all? So here comes another surprising result. So the whole project I'm talking about started with me finding a paper of Coxter. So Coxter is a very well-known mathematician, very highly kind of, I like Coxter a lot. And he had a huge bunch of work related to Coxter groups. And then he had a lot of works which are kind of known in the cluster algebra community. And the work I will talk about, I will mention, is exactly in between. And again, it's completely forgotten. So there are no quotes, it's hard to find online. And in this talk, in this work, he basically explains that there is a way to construct relate orthoschemes and configurations of points on P1. So his paper is a bit computational, and in the next couple of slides, I will explain kind of a way to understand it from modern perspective. So basically, what will happen? Okay, so let me just do it. So first, we don't want to talk about hyperbolic polytopes or spherical polytopes. We want something more general, something more algebraic. So I suggest a definition of a projective orthoscheme, and that's just a configuration of a smooth quadric in projective space and a collection of hyperplanes with the same orthogonality properties. So why it's a generalization? Because if you take, so this is a projective
connection between Q and the H's.
Sorry?
There's no connection between the Q
Yeah,
and the H's?
H, no connection, just any quadric and any hyperplanes. And here is an example, just a conic and three lines, and lines should be perpendicular with respect to the conic. So conic gives a scalar product, and they should be orthogonal. And if you have a hyperbolic orthoscheme, you pass to projective orthoscheme by just taking complexification. So hyperbolic space is a part of real space, it's a part of projective space over complex numbers. And faces in Klein's model of hyperbolic space just on hyperplanes. And the boundary, the ideal boundary, is actually a sphere, as we know. But if you complexify it, you will get a quadric, smooth quadric project. So basically, and the group of isometries is projective transformations preserving the quadric. So it's not surprising you can pass to this algebraic context without losing too much. If you want to compute just trigonometries, algebraic data. So so I will work with this object instead, and I will have a smoother result in this case. And so okay, so there is a theorem which unfortunately the name of the theorem is not here. So so the theorem it's kind of my theorem, but it follows Coxter's ideas, some of Coxter's ideas. It's kind of an attempt to understand Coxter's ideas. So the theorem states that there is a bijection between generic projective orthoschemes in projective space and configurations of n plus 2 points on P1. And generic is a very mild condition. Basically, hyperplanes are in general position, slightly more than that. You can ignore it. And the correspondence has properties that faces and angles of orthoschemes. They are also orthoschemes. And you can ask what configurations they correspond to. In the statement, they correspond to subconfigurations of your configuration. So there is a kind of a surprising way to see the whole business of configuration spaces and forgetful morphisms between them kind of realized as orthoschemes and taking angles and edges and faces. So that's a theorem. And here's an example. So in dimension 1, I just state what this correspondence does. And to a configuration of points x1, x2, x3, x4 in M04, it's of course, M04 is just a configuration space of 4 points in P1. I just have one invariant cross ratio, and I attach a segment of whose hyperbolic length is equal to this cross ratio. Sorry, whose not hyperbolic length, but tangent hyperbolic squared minus equals to the cross ratio. That looks weird. I mean, I understand. But I mean, in dimension 1, you have in both cases just one dimensional kind of you need to identify C and C, and you can do it in any way. Yes.
Sorry, you mean distinct points?
Sorry, could you?
Do you mean configurations of distinct?
Yes. Probably if you take non-distinct points, you will get some degeneration of orthoschemes. But this is not yeah, I mean, probably you can extend the series there, but this have not been done. Dimension 2 is a famous result of Gauss, also much less known than it should be. So it's called Gauss pentagramma mirificum, 1866. And the statement is as follows. So I will formulate it in spherical geometry because it's classical Gauss result in spherical geometry. And the statement is that if you take a spherical triangle with sides ABC and angles alpha pi over 2, 90 degrees gamma, then there exists a unique configuration of 5 points on P1, so that tangent squares of these 3 lengths of edges and 2 angles of the triangle are exactly 5 cross ratios of 5. So that's, I think, a remarkable result and very strange. And one thing which is kind of funny here is that you can ask, but there are different orderings of points, and I guess so we know what happens if you take another ordering of cross ratios. You get lambda, 1 over lambda, 1 minus lambda, 1 minus 1 over lambda, and so on. And you can ask what happens if you do it here. And kind of ironically, you will get, instead of tangent square, you will get all other trigonometric functions. You know, sine square, cosine square, tangent square, secant square, and cosecant square. And seconds and coseconds I have seen only in my grandmother's book on analytic geometry from 50s. So that's kind of a so this kind of correspondence between trigonometry and cross ratios is in a sense natural, but again, to me it was a big surprise. So that's the result of Gauss, and you can see here the theorem above, because basically 5 points corresponds to a triangle, and I said angles and edges correspond to subconfigurations, and so if you pass to subconfiguration, you will see exactly everything happens according to the rule. And that happens in general. So in the next slide, I want to give a construction. So of course, one wonders how to construct an orthoscheme, this geometric object, out of just configuration points. And so this I tried to understand for a long time, and the eventual answer is you need to use algebraic form of Maslov index introduced by Goncharov for some reason. So let me explain the construction. It's elementary, but it was again a surprise. So we start with configuration of points. So it should be n plus 2 in P1. And these are just n plus 2 lines in 2-dimensional vectors. So I need to construct a vector space of dimension n, whose projectivization will be Pn minus 1. Quadratic form is there, quadratic, and a collection of hyperbolics. So this is what I need. So a space is easy to construct. I just take vectors going along these lines with sum equal to 0. So kind of a balanced configuration of vectors. And dimension will be immediately n. That's easy to see. So that's a picture on the left. So then, if I take any triple of vectors, 3 indexes, I will have exactly one line in E, which is just triples of vectors going along these 3 lines with some zeros. They form a 1-dimensional space. Now I draw a combinatorial picture, which right now it's not clear why it's relevant, where I just draw a polygon and I draw a triangle for each triple of lines. So just again, it's just a picture. So here comes a result effect. There exists a unique quadratic, so you can think of quadratic form on E, with the property that 2 lines corresponding to a pair of triangles are orthogonal, if and only if triangles have common interior in the convex picture. So there is a unique quadratic form up to scalar, which kind of has a strange property. In particular, you can see here this Stashev Polytope associahedron in some way, because every triangulation will give you orthogonal decomposition of the space. So you kind of have a collection of orthogonal decompositions of your space corresponding to different triangulations of a polygon. And when you do a flip, it's kind of a sort of a move of 2 vectors inside a 2-dimensional plane. So of course, the natural question is, what is the formula for this quadratic form? And the answer is as follows. You take area form, which is just a determinant in 2-dimensional vector space, just xy, x1, y2 minus x2, y1. And then you take your vectors and you sum up the corresponding areas between the pairs of vectors. If you do a real picture, it will be actually usual area. And that's a form which is quadratic. And so this form was introduced by Goncharov. And in Goncharev's picture, you actually can do much more generally. You take a Lagrangian spaces inside a linear symplectic space, and then you take a similarly defined form, basically where instead of area you have symplectic form,
And in this way, you get a quadratic space out of a symplectic space and a collection of Lagrangians. And if you take its index in real case, you will get an algebraic version of mass. So that's a published remark of Kashivara. And Sasha Benison has a beautiful construction of this quadratic spaces form using some constructible sheet cohomology construction on it. So I'm not going to talk about that, but it's kind of beautiful. So in this way, I got now a quadratic and a space. I need hyperplanes. So this is what I do. I just take ears, sort of. So I take triangles which are adjacent to the boundary, and I take every except the two adjacent to the bottom segment, and now and the planes will be just there orthogonal. And you can see from the picture that you get an orthoscheme because consequent things intersect, so they are not orthogonal, but non-consequent don't intersect, so they are orthogonal. So you get an orthoscheme. And the theorem is that you get all orthoschemes in this way. So that's a one-to-one correspondence. Okay, so that's a story about orthoschemes. Can I move on? Any questions? So in this way, we get a pretty canonical, yeah, and by the way, there is an important reason why you can already see that this construction is relevant to the story of computing volumes. Remember, there was this delta angle in Lobachevsky form. So if you take 6 points, which corresponds to H3, this tangent delta squared, actually minus tangent, no, exactly, tangent delta squared, will be this product of cross ratios. I mean, you can understand that it's product of two cross ratios, kind of a product of two cross ratios is to cut your polygon in two. And that kind of explains that this angle, which was hard to understand, has a nice geometric meaning. This kind of can be seen here. Okay. So now I want to give a formulation of a formula of Lobachevsky. A formula that generalizes the formula of Lobachevsky to arbitrary space. So first observation. If volume would be a function on just the moduli space of points, for some reason it would be easy to find because it's easy to see volume as an iterated integral, and iterated integrals on configuration space are very well understood. I will come to that at the end of the talk. But actually, volume is a function on a finite covering of the space. So you need to take a covering where square roots of cross ratios have are well defined. Technically, it will be called level 2 spherical braid group. But it's just a 2 power something covering of M0 to n plus 2, and volume will be a function there, still multivariate. I mean, let me say just for like those who like this kind of approach. So actually, we have constructed a variation of mixed Scott state structures over M0 to n plus 2 finite covering. So this gives this variation of mixed Scott state structures, and we are going to explicitly compute it through structures coming from fundamental group of P1. So this is kind of a technical phrase for people who are working with this. So now I need, so formula will be pretty combinatorial, and I need a bit of combinatorics. So consider a polygon. So this even size polygons with 16 vertices is kind of, you can think of it basically being related to some order scheme. So we have an order scheme of higher dimensional space. We parameterize it. We take this polygon and we label it by points on P1. And then Q is a set of quadrangulations. So quadrangulations are, you cut your polygon into quadrilaterals. And there is a nice formula which is due to student of Euler, which is like analog of Catalan formula, which counts the number of quadrangulations. So so I take quadrangulation. Each quadrangulation defines for me a dual tree. So this is just a rooted tree with the root being this basic quadrangle. And in my formula later on, I will sum overall quadrangulations. So I will sum overall quadrangulations, something attached to a tree. And now for a tree, I need to write down a certain sum of polynomials. So this is a little bit more complicated. Let me just say kind of the partial answer. So actually, you need to use structure of Kohn-Kreimer-Hopf algebra of trees to write this map nicely. But in a first approximation, let me just write the highest
depth kind of terms. So if you have a tree, let's take a tree labeled by complex numbers. So then I want to attach to it a polylogarithm M of this tree. And this is basically sum of polylogarithms of these points, these numbers permuted, where I sum not over all permutations, but only on those which are kind of behaving well with respect to the tree. So if in tree, one vertex is on top of the other, sigma should respect that. So you sum over kind of all ways to order vertices of a tree so that this ordering agrees with partial ordering of the tree. And then there are some lower depth corrections. Oh, I don't want my Mac to go off charge. So, and this is an example. If you take simplest tree, just take polylogarithm. And if you take a slightly more complicated, you will start to get this kind of two trees coming from different orderings plus lower depth corrections. And you can write down explicit rules. It's not too hard. So now I can state the formula. So I consider my 2n plus 2 gon. Vertices are labeled by points. It gives me an orthoscheme. And I leave on this covering so I know all the square roots of cross ratios. So now I can label any tree corresponding to quadrangulations by roots of cross ratios. Not cross ratios, but roots of cross ratios. And then the statement is that to compute the volume of an orthoscheme, you need to sum over all quadrangulations this polylogarithm attached to this tree with square roots. And also you need to sum over monodromy with some character I'm not going to mention, but you need to kind of change signs of square roots in a certain way. And this gives a formula for. So here is an example. If you take Lobachevsky case, you see something which so elements here will be quadrangles over 6 gon, and it does not look like the formula of Lobachevsky, but actually it reduces that immediately if you just write a formula which expresses V1 once for V2, whichever mentioned, and you will get Lobachevsky formula immediately. So that's kind of this way, but it works in all dimensions. So unfortunately, I don't have time to explain the proof of it, which uses coproduct of multiple polylogarithms reduced to Goncharov, and on the level of polytopes, it gives you then invariant of polytopes, and then you can kind of merge these two things, and I mean, this is kind of how the story starts, but it's a long story how to prove the formula. So in the rest of the talk, I want to explain some applications, not applications, but like what else you can get from the circle ideas. Any questions? So the next story, I need to talk about the depth conjecture of Goncharov, which is related in some way to what we talked before, but you can think of it as independent subject. And then I will explain how they combine. So depth conjecture is the following question. When a sum of weight n polylogarithms can be expressed via polylogarithms of certain smaller depths. And the reason for it is very natural, because we like polylogarithms having smaller number of arguments because they're simpler in a sense. And so we want to know when polylogarithms with many variables, you don't need to use them, you can express them. And for instance, in weight 2, you can do that. And here's the formula. And this is why in dimension 3, volumes of hyperbolic polytopes can be expressed through just dialogues. And similarly, in weight 3, everything can be expressed through 3 logarithms. So this is why everything in dimension 5 can be expressed through 3 logarithms. And in weight 4, it's not longer true. So you need 2 functions, Li4 and Li3, So you need 2 variable functions. And that's why the Goncharov holds in H7, Li4 is not enough. So Goncharov gave a beautiful conjecture, which at that time was considered too optimistic, but now people start to believe it's actually true.
Wait. Just ask a stupid question. How do I know that Li3 and Li4 are really different from each other?
You need to know this coproduct. If you apply mixed Hodge theory there and compute this mixed Hodge coproduct, you will see immediately that one component of it equals 0 on Li3 and on Li4 everything is. Sorry, like you can do it in this way. So basically, yeah. Yeah. So you can do it in more elementary terms, studying monodromy ways, but modern ways is that.
Can you prove that they are independent in your stronger sense or not?
They are independent in any sense. They are linearly independent. You can plug in on.
In your sense, that you're going to express Li4 as Li3(1) plus something simpler.
Li4 you can express through Li3(1), but Li3(1) cannot be expressed through.
Or even in that sense, using or
Yes, using anything. Yes. So conjecture of Goncharov, I formulated very not precisely, but roughly it says that if you have a sum of multiple polylogarithms, conjecture of any element in arbitrary field, and you want to see whether they can be expressed through depths d or less, there is something you can compute called this iterated truncated coproduct. Something one can compute pretty explicitly. There is combinatorial formulas for that. If it vanishes, Goncharov conjecture predicts you can express your polylogarithm through lower depths. And if this conjecture were known, it has two remarkable corollaries. One of them is that if you take a volume of hyperbolic manifold, not polytope, then it should be expressed through classical polylogarithms. That's not known in general, and I think now one can prove it up to dimension 7. But I will mention it. But yes, that's not known. And the reason would be because hyperbolic manifolds have then invariant equal to 0, and then invariant is related to this kind of coproduct in the Goncharov conjecture. And the second conjecture is a famous Zagier conjecture that a special value of a zeta function of a number field in any arbitrary integer number can be expressed through Lien. And only through classical polylogarithm. It's more precise than that, but that's basically the statement. And again, for the same reason, the coproduct there has to do with Martini coproduct, and the Zagier conjecture has to do with x1 in the category of motives. So basically, this is where the reason comes from. So both these cases, the statements are kind of known up to n equal to 4. For n equal to 2, it's original results of Zagier. And for n equal to 3, it's a result of Goncharov, and for n equal to 4, it's our work with Goncharov, and for n equal to 5 and more, it's 4. So, but there is an interesting fact that if you take depths less or equal than half of the weight, then this Goncharov criterion is completely empty. So there is nothing to check. Everything vanishes. And so for a long time, this was a question that you can express any polylogarithms or polylogarithms of half of the weight. And so when I started to work on that, it was hard to believe because the best known result was that you can reduce weight by 2. So that's can be equal to n minus 2, which was the result of Francis Brown. And the Goncharov conjectures predict n over 2. So now I'm going to explain the theorems that actually that's the case. And the proof is by explicit formula, and this formula is more or less the same as Lobachevsky. So that's kind of the surprising relation to subjects, and I have no conceptual understanding of why this story works as it works. So, okay, any questions? Okay, so consider configurations of points on M0 to n plus 2. So we had a formula, this formula for volume of our orthoscheme, and it has this polylogarithms of square roots of cross ratios. So for those who are working with polylogarithms, idea to plug in square roots of cross ratios seems to be very strange because they are, I mean, cross ratios have a nice factorization properties, and why you take square roots. So the natural thing is to take not square roots, just to take usual cross ratios in the same positions. And then you get a certain function of this 2 n plus 2 points, which will be a sum of polylogarithms. And I just write exactly the same formula, except you don't have this monodromy anymore, so you don't have signs and no square roots. And this will not be 0, but it will be a certain function. And again, technically speaking, it's a variation of mixed hot state structures over the configuration space that we know the company. So what is interesting is that function has a weight n plus m, which can be anything, because in this formula for m over 3, I was allowed to like plug in any m. And so it has fixed depths, but arbitrary weight. And if you take the simplest example, it will just give a classical polylogarithm of cross ratio. So it's kind of a nice object. If you take the next case, it will be a certain pretty explicit sum of depths 2 polylogarithms. And here you can see pairs of cross ratios corresponding to 3 quadrangulations of a 6 formulas. 3 ways to cut it into 2 formulas. So
now I need to state a property of oh, I have time. I need to state a property of this quadrangular polylogarithms, which is the key. So let me maybe say it formally, and then I will state more formally. So this is a function on the configuration space M0 to N+2. And you can ask, what is its monodromy, where it's multi-valued, and so on and so forth. And if you look at each term here, it's this multiple polylogarithms. Multiple polylogarithms have a kind of a complicated multi-valuedness as a point where you have products of arguments equal to 1. So this product of cross ratios equal to 1 will be certain divisor inside the moduli space, which is not on the boundaries, it's inside. But if you take this particular combination, then somehow this multi-valuedness cancels out, and you have a function which has this multi-valuedness only as a boundary of the configuration space. So that's kind of a key property. So to formulate it more explicitly, let me say that. So consider M0n. Now I take arbitrary number of points. And on that, I can consider what's called Hopf algebra of Chen iterated integrals. So a lot of people in this department know and like homology of M0n related to this harmonic algebra of colored traits. Basically, H1 is generated by forms d log of cross ratio. And this Hopf algebra is Koszul dual to this homology algebra, and it can be explained pretty explicitly. So, but I mean, that starts to be a little bit more technical. So you take this bar complex, and this is just tensor products of these forms. They lie inside the vector space, which is tensor product of H1. And you take such linear combinations which have a property that if you take any intermediate index and you wedge forms there and don't change anything else, you get 0, and that's true for arbitrary intermediate. So it's actually a property of iterated integral on a variety to be independent on a particular class. So it's homotopy invariant. It's kind of a de Rham differential on iterated integrals. And theorem is that this quadrangular polylogarithms actually lie inside the space of iterated integrals. And what it means, it exactly means they don't have any monodromy on some bad divisors inside the moduli space. They are just. So you can, in a sense, it means that there is a much more simple way to express them, and you can express them in this iterated integral of this tensor products of log cross ratio forms. So and that's a harder statement. And moreover, the space is spanned by these objects, and it's spanned by actually quadrangular polylogarithm with depth n and weight 2n, and depth n and weight 2n+1. So the reason why, so after you know these elements are iterated integrals, the space of iterated integrals is easily structured because of this casuality property, and so you can easily prove anything there. After you know there's there, it's easy to show that all the space is spanned by these elements, and then you can express just basic iterated integrals through them, but then you can express multiple polylogarithms through them. And so this gives the proof of the depth conjecture. So you can show that multiple polylogarithms can be expressed through iterated integrals. It's really simple. But then you can express any iterated integrals through exactly these functions which have depth being half of the weight. So so essentially one needs kind of some linear algebra on this in the space plus this quadrangulation form. So in the last kind of couple of minutes, I want to talk about cluster polylogarithms. So at this moment, we see that this quadrangular polylogarithms coming from Lobachevsky formula are fundamental objects. And of course, it's natural to understand how one can understand them more conceptually. What are they? Suppose we don't know about this computational volume question, where you might see them coming from somewhere else. So now I want to kind of talk about the last part of the story. It's a joint work in progress with Andrei Matviekin. So cluster polylogarithms. So here is a definition, and we define this cluster polylogarithms in big generality of any cluster variety, but I just need it on M0. And here it can be very explicit. So let's look at my points. in M0n configuration of points and likely cyclically ordering it. So then cluster polylogarithms will be elements of the space of iterated integrals, which have a property that it can be expressed as a sum of this d-logarithm of differences of points, where in each term, the chords corresponding to these differences are pairwise not intersecting, like have no common interior chords. So basically, there is certain triangulation, and they underline their chord of this triangulation. So this condition is very strange because you, on one hand, need this previous condition of integrability, and on other hand, you need this condition of basically some combinatorial restriction. And you might think that you will get just empty space, or you will get nothing interesting. But the fact is that actually you have a space which is very well behaved. So first you can compute its dimension, and it's increasing with the weight up to some point, and then it stabilizes. And also it's kind of interesting, the dimension grows polynomially in weight and in m actually, unlike the dimension of the space In, which grows exponentially. So iterated integrals grow exponentially, like more or less free the algebra on n-2 generators. And cluster polylogarithms is a small subset inside, which is very well behaved and grows polynomial. And moreover, if you take quadrangular polylogarithms of points and order the indices so that they increase, you will get a generating set of systems. So, and this more or less defines these functions uniquely up to lower depths, and you can understand them pretty well. So, from here, one can expect that if you take higher, like other manifolds, then you also can probably understand all cluster polylogarithms on higher varieties. And now we are trying to understand cluster polylogarithms on Grassmannians and on high varieties, and so on. For instance, one can show that higher motivic Chern classes can be expressed through this multiple polylogarithms, cluster polylogarithms on Grassmannians. So that is kind of work in progress. But this all results have another application. So now I'm coming back to kind of the original, the beginning of the talk. So as I said, this functions span the space of cluster polylogarithms, but there are relations between them. Surprisingly, these relations are very easy to understand. So this is the formula. If you just take this quadrangular polylogarithm of all subconfigurations with certain signs, it's a sum up to 0. So that is easy to prove relation if you express them as iterated integrals. But if you plug in inside the formula using quadrangulations, so this polylogarithms of cross ratios, this gives you a functional equation for multiple polylogarithms, which is nonlinear and is kind of interesting. And if you take this case for 5 points and weight 2, you will get immediately the Abel's 5-term relation, which is not surprising, the sum of dilogaritms. If you take the same thing in weight 3 and 6 points, you will get Kummer's equation and 22 Goncharov terms equation immediately. They can follow from here. And if you take Q7-4, from here you can relatively easily prove the depth conjecture, the full one, not the half one, which I expressed before. The full depth conjecture in weight 4, and you can get from here again relatively easily the 900 term equation of Lamb. If you take weight 6, we were able to prove some parts of the depth conjecture in weight 6, but it's again work in progress. But we kind of proved the analogs of the Gundel's formulas there. We conjectured that all functional equations for multiple polylogarithms follow from this. And moreover, so just again, last kind of phrase. So Goncharov conjectures go further, and using functional equations, Goncharov defines a certain Lie coalgebra of multiple polylogarithms, and conjecture is the same as the coalgebra of mixed state motives over arbitrary fields. So this is a Goncharov explicit formula. And so basically, to give a again conjectural explicit formula expressing what this coalgebra looks like, you need some way to state what are equations between multiple polylogarithms. And one can take this and conjecture that this is an explicit formula for the coalgebra of mixed state motives. And of course, it's a very
I mean, in sense, it's optimistic, but it agrees with all results we had so far. Last thing is that what we are trying to do now is we are trying to use these functional equations and work like to generate points, go to the boundary of the Riemann space and so on, to get other parts of the depth conjecture. And it seems that it works out, but maybe one needs to look at cluster polylogarithms of higher varieties of Riemannians to be actually able to go to deeper layers. So we are now trying to do the intermediate depths being slightly less than half of the weight. But this is work in progress. Thank you very much.